There are 400 billion stars in the Milky Way alone. And beyond our galaxy, the observable universe contains somewhere in the range of 2 trillion galaxies. When you do the arithmetic, the number of stars that have ever burned in the history of the cosmos climbs past the total number of grains of sand on every beach and desert on Earth. It is a figure so large that it strips language of its power to convey meaning. And yet, as of this moment, despite decades of listening, searching, and scanning the sky with instruments of extraordinary sensitivity, we have not received a single confirmed signal, not one verified message, not one unambiguous trace of a mind somewhere out there looking back at us. The silence is total, and it is deeply, profoundly unsettling. This is the problem that the physicist Enrico Fermi captured in a single question over lunch one afternoon in 1950. If the universe is this vast, if the numbers of potentially habitable worlds are this astronomical, then where is everybody? That question, deceptively simple on the surface, has resisted resolution for more than 70 years. And the more carefully physicists and astrobiologists examine it, the more they begin to suspect that the answer is not a technological one. It is not that we simply need a more powerful radio telescope or a more sensitive spectrometer. The answer may run deeper than that. It may cut into the very structure of how complexity arises from simplicity, how life bootstraps itself from chemistry, and why the transition from biological life to technological civilization may be among the rarest events in the entire history of the cosmos. To begin to understand why the universe might be effectively silent, we have to walk through what scientists call the Drake equation. Frank Drake proposed it in 1961 as a way of estimating the number of communicating civilizations in our galaxy. The equation multiplies together a sequence of probabilities. How many stars form each year? What fraction of those stars have planets? What fraction of those planets are habitable? What fraction of habitable worlds actually develop life? What fraction of life-bearing worlds produce intelligent species? What fraction of intelligent species develop technology capable of sending signals across interstellar space? And finally, how long such a civilization broadcasts before it either destroys itself or goes silent? Each of those terms, when astronomers first filled them in, seemed optimistic. The result suggested a galaxy teeming with minds, yet we hear nothing. The problem is that those early estimates were infused with a kind of invisible optimism. We assumed almost unconsciously that life is what the universe does when conditions are right. That given liquid water, carbon-based chemistry, and a stable sun, biology is almost inevitable. But the more deeply biologists peer into the origin of life, the more that assumption looks shaky. Life did not simply crystallize out of a warm puddle the way salt crystals form in an evaporating solution. The origin of life required something far more improbable. It required the spontaneous assembly of self-replicating molecular machinery of breathtaking complexity. The ribosome alone, the cellular machine that reads genetic code and assembles proteins, is a structure of such engineered precision that it staggers the imagination of molecular biologists who study it daily. And we have no idea how the first ribosome or anything like it came to exist without a prior ribosome to build it. Think of it this way. Imagine you are given a box of all the components needed to assemble a watch: springs, gears, a face, hands, a winding mechanism. If you shake that box randomly, the components will never assemble themselves into a functioning timepiece. Not in a year, not in a billion years. The watch requires something that random thermal motion cannot provide, which is a process that selectively builds toward function. Life solved this problem. Darwinian evolution is exactly that selective process. But evolution can only begin once you already have a self-replicating molecule. Before the first replicator, you are shaking the box. And the question of how the first replicator assembled itself spontaneously from raw chemistry remains one of the deepest unsolved problems in all of science. There are researchers who believe this first step, the origin of simple replication, may actually be easier than we think. Certain organic molecules called nucleotides have been shown to assemble into short chains under specific geological conditions, around hydrothermal vents, or in the presence of particular mineral surfaces. There is genuine laboratory progress here. But even granting the easiest possible origin of simple replication, what comes next is perhaps even more demanding. At some point, the transition from scattered self-replicating molecules to a genuine living cell with a membrane, a genetic code, a metabolism, and a division between information storage and protein synthesis had to occur. Each one of those innovations individually is extraordinary. Their coordinated emergence in a single lineage once is the event we call the last universal common ancestor, and every living thing on Earth descended from it. Every bacterium, every mushroom, every whale, every blade of grass, one ancestor, which means it may have happened exactly once in 4 billion years of planetary chemistry. That is not a reassuring statistic. Now layer on top of this the second great filter. Even granting simple life, the jump from single-celled organisms to genuinely complex multicellular life took another 2 billion years here on Earth. 2 billion years of bacteria and archaea, single cells doing their biochemical business before the first complex eukaryotic cell appeared with its internal compartments, its mitochondria, its elaborate chromosomal machinery. The merger that created the eukaryotic cell, one bacterium being engulfed by another and the two becoming a permanent partnership, appears to have happened exactly once in Earth's entire biological history. Every complex life form you can see with the naked eye, every animal, every plant, every fungus descended from that single symbiotic event. Again, the sample size is one. And then there is the step that concerns us most directly. The emergence of what we would call technological intelligence. Life on Earth has been present for roughly 3.8 billion years. Complex multicellular animals have existed for perhaps 600 million years. Homo sapiens, our species, has been around for roughly 300,000 years. Technological civilization, the kind that can build radio telescopes and send probes to the outer solar system, is perhaps 200 years old. That is 200 years out of 3.8 billion. If you compress the history of life on Earth into a single calendar year, human technological civilization would occupy the last 2 seconds of December 31st. And we are asking why intelligence capable of broadcasting its existence seems so rare in the galaxy. The answer may simply be that the sequence of improbable steps required to produce it is so long, and each step so individually unlikely, that the expected number of times it happens anywhere in the observable universe might be close to one. This is the logic behind what the Oxford philosopher Nick Bostrom and others have called the Great Filter. Somewhere along the chain of events from sterile chemistry to spacefaring civilization, there is a step so improbable, so demanding, that virtually every planetary lineage fails at that step. The chilling question is whether we have already passed through that filter or whether it lies ahead of us. If the filter is behind us, if the origin of complex eukaryotic cells was the great improbable bottleneck, then we might be genuinely alone, the first civilization in our corner of the universe to make it this far. That would be lonely, but it would be hopeful. It would mean that our future, while not guaranteed, is open. But there is another possibility, and physicists and astrobiologists discuss it with a particular kind of unease. What if the great filter lies ahead? What if the bottleneck is not in getting from chemistry to civilization, but in sustaining a civilization beyond a certain threshold of technological power? Every civilization that reaches our current level of technology eventually develops weapons of mass destruction, or triggers runaway environmental collapse, or succumbs to some technological accident of a kind we have not yet imagined. If that is true, then the silence of the universe is not evidence that life is rare. It is evidence that technological civilizations tend to be brief. They bloom, and then they vanish before they have time to send even a single coherent signal that could cross interstellar distances and reach a receiver that is still listening. The distances themselves impose constraints that are easy to underestimate. Even if we detected a signal from a civilization 1,000 light years away, that signal would have been sent 1,000 years ago. The civilization that sent it might not exist anymore, and our reply would take another 1,000 years to reach where they once were. Communication across interstellar distances is not a conversation. It is archaeology conducted at the speed of light. By the time a message completes a round trip between two stellar systems, civilizations can rise and fall, evolve into something unrecognizable, or disappear entirely. And the speed of light itself is the wall that physics places on all of this. General relativity is merciless on the question of faster-than-light travel. The geometry of space-time does not permit it under any known physical law. Wormholes, which are solutions to Einstein's field equations that connect distant regions of space-time, would require a form of matter with negative energy density to remain open and traversable. We have never observed such matter in nature. Quantum field theory hints at the possibility of negative energy densities in extremely constrained laboratory conditions, the Casimir effect being the most famous example. But scaling that phenomenon to the size required to hold open a traversable wormhole is so far beyond any technology we can conceive that it belongs firmly in the domain of speculation rather than engineering. The universe offers no shortcuts. Light speed is the ceiling, and at light speed, the galaxy is 100,000 years wide. Even the search for radio signals, which has occupied the SETI program for more than 60 years, carries hidden assumptions that may no longer hold. We have been listening on radio frequencies because radio is what we ourselves used to communicate at long range for most of the 20th century. But a civilization that is even a few hundred years more advanced than we are would likely have moved beyond radio. Their communications might be encoded in neutrino beams or quantum-entangled photons, or some physical medium we have not yet discovered. We might be like an islander on a beach listening for the sound of drumming from distant shores, while the actual messages are being sent by satellite uplink on a technology the islander has no framework to detect or interpret. What is perhaps most disorienting of all is what physicists have come to call the problem of self-selection. We are not a random sample of intelligent civilizations. We are one specific civilization that exists at one specific moment in cosmic history. Our very existence as observers is a data point that is selected for by the fact that we survived long enough to do the observing. This is the anthropic principle applied to astrobiology, and it cuts in unexpected ways. It means we cannot simply argue that because we exist, intelligent life must be common. Our existence was necessary for us to ask the question, but it tells us nothing reliable about how common our situation is. We are, in the language of probability theory, a biased sample. We are the survivors, and survivors always underestimate how dangerous the path was. None of this is to say that life does not exist elsewhere. The molecular building blocks of life, amino acids, sugars, nucleobases, have been found in meteorites, in interstellar gas clouds, in the atmosphere of distant moons. The chemistry of life appears to be genuinely cosmic. Water, that most essential of solvents, exists in liquid form on at least several moons in our own solar system. Europa, the icy moon of Jupiter, has a subsurface ocean in contact with a rocky seafloor, the exact environment where hydrothermal chemistry might generate the energy gradients that biology could exploit. Enceladus, a moon of Saturn, actively vents water vapor and organic molecules into space. Mars almost certainly had liquid water flowing on its surface for hundreds of millions of years in its early history. The stage for life has been set many times in many places. What remains so uncertain is whether the performance ever begins. The honest answer, the one that physics and biology together compel us toward, is that we do not know. We do not know whether life is common and intelligence is rare. We do not know whether intelligence is common and longevity is rare. We do not know whether we are nearly alone or whether the galaxy is a vast, quiet archive of ancient ruins left by civilizations that blazed and burned before the Earth had even formed. What we do know is that the question is not trivial. It is not a question that can be answered by wishful thinking or by the sheer size of the numbers involved. A universe of 2 trillion galaxies is still a universe governed by physics. And physics is ruthless about what it permits and what it forbids. The silence, for now, stands. And it asks something of us, not despair, but clarity. The fact that we have not found others does not diminish the significance of what we are. It amplifies it. Every mind that has looked up at a night sky and tried to understand what it is looking at, every civilization that has built instruments to extend its senses beyond the limits of its biology is doing something that the universe may do extremely rarely. That is worth sitting with. Not with vanity, but with a deep and serious awareness of what it means to be a pattern of matter that has become conscious of the cosmos that built it. Whether or not we are alone, the fact that the question can be asked at all, that physics can be understood, that mathematics can describe the curvature of space and the decay of atomic nuclei, is itself a phenomenon that demands our fullest attention. Because if intelligence is rare, then every mind is precious. And if it is precious, it is also fragile. And if it is fragile, then what we do with it, how we sustain it, how we protect it from the filters that may lie ahead, is perhaps the most consequential problem we have ever faced.